So the next thing that we're going to be talking about is Gauss's law. And more importantly, we're going to be using our knowledge about densities and how we can use that to solve a problem. So I'm going to do the same thing how I always do with my little chart with my algorithm, and then we can go from there. So first thing we're going to do is we're going to read it, and I'm going to kind of go and do all together the underlining buzzwords and reading at the same time, but I'll be kind of going a little bit slow. So a non-uniform but spherically symmetric distribution of charge has a density rho r as given as follows, where rho naught is a constant. And then we're given the equations for when r is less than big R and when r is greater than big R. Total charge contained in the charge distribution, obtain an expression in the electric field in the region R is greater than big R, and obtain an expression for the electric field in the region R is less than big R. Okay, so a lot of words, but let's remember what we're doing here, and let's draw a picture out first. So two buzzwords that should help you know what this distribution looks like, or what this looks like, is it says non-uniform but spherically symmetric. So we don't really care about the non-uniform just yet, but spherically symmetric should let you know that this is a circle, or it's a sphere. So I'm going to draw a circle, and I'm going to label it, let's say this is the center, and this is big R. Okay, and it says that it has this charge distribution, and it's given in the form of two equations. So when R is less than big R, so if we imagine like a little surface like this, and we go here, that has little r, the first equation is what we're thinking of. So let's number these. So 1 and 2. And then if we are outside R, so if we're out here, we have the second equation. So it wants us to find the total charge contained in the charge distribution. So this is not even thinking about electric fields yet. We are solving for Q. So from before, we know that when we see rho, it generally means that has a volume density, so volume charge density. So since we are finding the total charge density, we want to find the total charge that's contained from the very inside all the way out to infinity. So since our little r is not defined to a particular radius outside of big R. So basically what we want to do is we want to integrate, I know, big word, kind of scary, from 0 to infinity, the charge densities in the form of equations that were given. So let's talk about how we would want to do that and some little tips and tricks of what to do. So from 0 to R, we're given this equation. I'm going to do a different color right here, but we're given this one right here in yellow. And it has some values to it. And it says for R less than R, big R, but we're gonna, since we want to find the total charge contained in the charge distribution, we're gonna integrate from 0 to R. So the first thing that we want to do is we want to set up some integrals. We don't know what we're doing yet, but we know that this first one is we're integrating from 0 to R, right? and it's going to be equation 1, because equation 2 is not defined from 0 to big R. It's only included for outside. And we don't know what we're integrating over yet, but we know that it's a volume charge density. So let's integrate over the volume of this space. So I'm going to write dV. So just to be clear what I'm doing, we're trying to find the charge, and we are given a charge density, and we know that it's a volume charge density. So our volume charge density for the first equation is rho r equals rho naught in parentheses 1 minus 4 little r over 3 big R. And that's valid for all values from 0 to big R. And so since that is a volume charge density, and we want to find the charge, remember, just generally speaking, rho is equal to Q over V. Generally speaking, we want to multiply our charge density times our volume. But the problem is that as we are going from different radius, it will change. Our charge is going to change as we increase our radius. So even though we know what generally speaking, what our volume is, we don't know what will happen as we increase our radius. So to combat that, we want to integrate over the volume so we can figure out how that radius is changing. So then we want to integrate from R to infinity, and that's going to be our equation 2 and also dV. And also, okay, so now let's look at this first integral and the first thing that we want to do and define. So if we are so now that so what I'm going to do next is I'm going to erase this so that we can kind of have more space. Okay, so we still have our sphere that we drew. So let's just focus on this first problem that we're doing, on this first integral. So we know that it is spherically symmetric and it's non-uniform. So if we think back to this, to the video that I did, if you remember, I drew a sphere and I kind of it was kind of like a cross section of it. And the inside had a lot of charge in it. And then as you increased it, it got less and less and less. So that's kind of similar to what we're doing here. But we're kind of doing it because we don't really exactly know what it's going to look like, because we're just given an equation for the charge density. But we do know that it is changing with the radius. So as little r increases from the center outward, it is changing. Okay, let's look at that dV in the first integral. So we know that generally speaking, if we were looking at a rectangular prism and we wanted to know its volume, we would say, okay, well, and let's say it's length times width times height. Okay, so if we were looking at a rectangular prism, we would know, okay, it has some length L and some width W, and it has a height H. So we know that volume is length times width times height. But what if I wanted to define it and only use this one face? And let's say I knew the area of that face. It's right there. How would I want to define the volume? Well, then we would want to say, well, since it is length times width times height, and we're defining the area, and we know what the area is, it's A, and we know that this right here is also L. and the area is just H times L, I would say that the volume is just A times the width. Right? Does that make sense? We could do that with any one of the faces, right? So let's think about that with the sphere. If we know that we want to try and find the volume, but we know that the only thing that's changing in this charge density is the radius. What if we defined the area of the sphere that we know, say we know that it's this radius right here, R. And then let's say we want to know what the full sphere is, the full volume of the sphere. But we know that the charge density is changing as we increase that radius. So what if, to counteract that, we say we want to find, okay, that dV is equal to the area of that sphere that we have with radius R times dr. So as we're increasing that radius, so we know that there's some change in radius. So when we do our integral, we are only looking at that change in radius because that's what our charge density is dependent on. So what's the area of a sphere? It's 4 pi r squared. For some radius r, we don't know. And so our dV is just going to be 4 pi r squared dr. So now let's look at this first integral. So we have our q is equal to, from 0 to r, our first equation is rho naught 1 minus 4r over 3r. And when we do dv, it's 4 pi r squared dr. And that is our first integral. Now, same thing with the second one, but what is different about the second one is that, well, when we're integrating from r to infinity, which is the total charge distribution, because we're not given what this r is, our second equation that defines what our charge distribution is outside of our big R radius, it's 0. So if we're integrating over 0, that just goes to 0. So we don't have to worry about that for our total charge distribution. So we have a lot of constants out for this one. So let's solve this, right? So I'm going to move this down a little bit. So we have Q is equal to, I'm going to take out the 4 pi and the rho naught because they are constants in our integration. And we're left with 1 minus 4r over 3r r squared dr. So I want to distribute that r squared into our integral. So I'm just going to be looking at this right here. So I'm going to take the constants and leave them out for right now. And I'm just going to be focusing on solving the integral, but I'll put them back in at the end. So we have r squared minus 4r cubed over 3r dr. Okay, so now we want to solve this integral. We want to integrate it. And we're still integrating from 0 to r. So now let's do the integral. So I'm going to make this r squared dr minus 4r cubed over 3r dr. So I split them up into two separate integrals, and now I can do my anti-differentiation. So the integral of r squared is 1/3 r cubed. And then for this one, this one has a r cubed. Notice that the big R has nothing to do with the anti-differentiation. So we can just take that out as a constant, but I'm going to leave it in here just so that we can kind of just get going on this. So since this is r cubed, I'm going to do 1/4 4r to the 4th over 3r. And this is evaluated from 0 to r. So automatically, I'm going to take out that 1/4, and now we are left with 1/3 r cubed minus r to the 4th over 3r, all evaluated from 0 to r. So now let's bring back so remember this is q equals, and we have that 4 pi rho naught. So now let's bring in let's add our bounds in. So RQ is equal to 4 pi rho naught. We start with the higher bounds. So we have 1/3 r cubed minus r to the 4th over 3r minus 1/3 0 cubed minus 0 to the 4th over 3r. So automatically, since these are zeros, we can automatically cancel that out, and that goes to 0. So let's look at this first part now. So automatically, I can see that these two big r's in the second term cancel out. So this to the 4th turns into a 3. So this right here turns into 1/3 r cubed minus 1/3 r cubed, which just equals 0. So the total q in this distribution is 0. I know, a little bit anticlimactic, but so that looks at when we're integrating from 0, the very, very inside, all the way out to r, big R. That does not mean that when we are inside our charge distribution, that there will not be any charge, and we'll get to that in our next part. So now let's talk about B. It says obtain an expression for the electric field when R is greater than big R. So let's write down Gauss's law, which is what we'll be using to solve equations like this, solve problems like this. So Gauss's law says that the integral of E dot dA is equal to the enclosed charge over epsilon naught, which is just a constant. So let's look at the region when R is greater than R. It's telling us that the charge distribution is 0. So if the charge distribution is 0, that means that Q enclosed is 0. If there is no charge enclosed, that means that we have no electric field. So in R is greater than R. So that is our final answer. If there's no charge enclosed, no charge distribution enclosed, that means that we do not have an electric field, and it is as simple as that. So C wants us to look at the region when R is less than R. So remember, if we have our sphere right here, it's asking us for, if this is big R right here, it's asking for some little r right there. So what we're going to do, the first thing that we should do is enclose a Gaussian surface in this area that we are imagining. And so in this case, it's R is less than big R. So what I'm going to do is enclose our Gaussian surface just like that. It's not a circle, but it'll do just fine. So we can imagine that our Gaussian surface has some radius r inside our charge distribution. So let's write Gauss's law. So for C, we have E dot dA is equal to Q enclosed over epsilon naught. So since I kind of went through our total charge distribution a little bit fast, let's redo our Q enclosed calculation, but let's just do it instead of integrating our bounds from 0 to R, let's do it to big R, let's do it from 0 to little r. So what we're trying to do is find how much charge is in this radius R that we defined. So our Q enclosed is equal to 0 to little r, rho naught 1 minus 4 r over 3 big R dv, and we know our dv is some 4 pi r squared times dr. So let's take out the 4 pi and the rho naught, and let's do this integration again. So that's going to be equal to 4 pi rho naught from 0 to r 1 r squared minus 4r cubed over 3r dr. So now let's keep this in terms of the little r, but we're still integrating over little r. So our bounds are from in terms of little r, and we're differentiating it and we're integrating over little r. So it's a little bit confusing, but hang on tight. So what we're going to do is we're going to integrate again. So we have 4 pi rho naught is equal to 1/3 r cubed minus 1/4 4r to the 4th over 3r evaluated from 0 to r. We know that the lower bounds when evaluating at 0 are just 0. So let's just plug in our regular little r. So immediately we know that this 4 cancels out. And we're just left with that the Q enclosed at some radius r between 0 and big R, it's just some little radius r, is 4 pi rho naught 1/3 r cubed minus r to the 4th over 3r. Let me redraw. And that is our enclosed charge. So at some radius r, it doesn't matter, some little radius r, we can define our Q enclosed like this. So that's great. So let's go back to our Gauss's law equation and let's talk about this E dot dA. So if we can imagine that this electric field is going outwardly, it's expanding radially, we can draw our field lines. I'll do it a different picture. It's drawing our electric field is like this. It's expanding outward radially. And we want our dA to be in the same direction as E, because our goal is to make sure that E becomes a constant. And the only thing that we're integrating over is that dA. So what does this mean? Let's do a little aside. So let's say I have this sphere, just like we're doing in this problem. And it has electric field lines that look like this. What it means to have our electric field lines and our area vector in the same direction, if we were to draw a little circle like this, the normal vector of this area that we drew would be in the same direction as our electric field. So if our electric field is in blue and we want to understand what our area vector is, we would just draw vectors that point out radially from the surface that we drew. So these are called normal vectors. So if you can imagine a sphere and we just drew a whole bunch of vectors from every little point that we could think of, those are all normal vectors from the surface, from the area of the surface that we drew. So you can realize that in this case, our electric field and our area vectors are in the same direction. So when we write our E dot dA, our electric field and our area vectors, if they're going in the same direction, that just becomes E dA. That looks like an epsilon. It just becomes E dA, because no one likes to work with vectors when you're integrating. So this is only possible if they are going in the same direction. So now our E is just a constant. We don't know what our electric field is, but we can assume that it's constant. So now we can bring this E out of the integration, and we're left with dA. So most of the time we know what surface we are creating. We know what that surface area is. So in this case, if we had a little sphere inside a bigger sphere, the dA would just be the surface area of a sphere. So for this case, it would become E 4 pi r squared. So it is recognizing that our electric field and our dA vectors, which is just normal vectors that we create from the surface that we created, our Gaussian surface, and realizing that if they're in the same direction, this dot product right here goes away. Because they're going in the same direction, it just becomes the magnitude of the vectors. So it just becomes E and dA. But E normally has nothing to do with the area that we are enclosing. So we can take it out of the integral, and our dA is just the integration of a whole bunch of tiny area pieces. So if we integrate over a bunch of tiny area pieces, we're left with the area of that particular surface. So in this case, if we're integrating over a sphere, it is the surface area of that sphere, which is 4 pi r squared. So we now know that we are integrating over a sphere that we created of radius r, which is right here. And if we drew our dA vectors, they would look just like that. So we know that they're in the same direction as our electric field, which is in blue. So E dot dA just becomes E dA. So let's finish this down here. So if we have our E dot dA equals Q enclosed over epsilon naught, our E dot dA just becomes E dA. And E becomes a constant, which is what we are solving for. So now we are just integrating over dA. So if we are just integrating over dA, we take a bunch of little tiny area components of our bigger sphere that we made, which is a sphere. So if we take little tiny area sections of our surface that we created, that we defined as our Gaussian surface, which in this case is a sphere, we can just say, well, I know what the surface area of a sphere is. It is just 4 pi r squared. And then we have our Q enclosed. So we have it right there. So I'm going to define it as 4 pi rho squared, all multiplied by 1/3 r cubed minus r to the 4th over 3r. And this is all over epsilon naught. So now we want to solve for E. So let's divide this 4 pi r squared on the other side. So if we divide 4 pi r squared, that's the same as multiplying 1 over 4 pi r squared. So let's see what that cancels out. So that cancels out the 4 and the pi over here. And then over here where our r is defined, this r squared cancels out the r cubed and it just becomes r. And then for the r to the 4th, we have that it becomes r squared. So finally, our E is rho naught over E naught, 1/3 r minus r squared over 3 big R, and that is our answer. So that concludes our Gauss's law video, but if you want a little bit of a challenge after solving this problem, I have some extra problems for you if you want to take a gander at them. So the first one is to graph the electric field E as a function of R. So how would you graph the electric field at both from R equals 0 to R equals infinity? And then some calculus problems for you. Find the value of R where the electric field is at a minimum, and then find the value of the electric field when it is at a maximum. So that wraps up the problem for today. I hope this was helpful, and I will see you next week.